Fantastic. Well, it's a pleasure to be here. Thank you so much for having me. I'm coming from Mila, as you said in the kind introduction. And so I'm a computer scientist. So please call me out for those I know who are coming from other backgrounds if I'm either using too much jargon from one field or not enough in another. I also just I'm still getting my head around some of the concepts in material science, so apologies in advance if I say anything that is inaccurate from the application perspective. As a little introduction to my group, we work on machine learning for climate action across many different kinds of settings. So you can see a couple of those there. This is some automated sensors for identifying moths, for scaling up biodiversity monitoring. Here is some just temperature maps of the world. But we work on a lot of different things in machine learning for climate action. Everything from gathering information, including biodiversity monitoring, carbon stock estimation, so understanding where trees are in a forest, how old they are, how much carbon is being stored. Improving operational efficiency. So that can take many forms: power grid management, operating electrical grids to waste less energy, or controlling heating and cooling systems in buildings so that they are more efficient, so industrial HVAC systems. Forecasting is another way that we use machine learning to help accelerate climate action, including predicting agricultural yields, so taking satellite images of agricultural land and predicting what the yield is going to be for particular crops to guide to improve food security in a changing climate. And then speeding up simulations. So for example, we've worked extensively on approximating particularly slow pieces of climate and weather models, which are extremely accurate. We know how the climate is changing and how the weather works, but sometimes these are extremely slow to run, which is a theme that we'll see again today. And then the fifth theme, which is what we're going to be talking about here, is accelerating scientific discovery. So helping use machine learning to guide the process of discovering new materials or new experimental parameters in contexts relevant to climate action. So the motivation for the particular problem that we're working on here is motivation that's doubtless very familiar to many folks in the room. So currently, fossil fuels are required for many settings in heavy industry and transportation. These are so-called difficult to decarbonize sectors. There are settings in which fossil fuels are providing the energy, but in some sense, that is easier to decarbonize if it's fossil fuels going to electricity than it is fossil fuels being used directly in various settings. So transportation, fossil fuels are extremely energy dense, so they're very difficult to replace with batteries, certainly in things like long-distance transport that can't be recharged or planes. And in heavy industry, there are many settings like the Haber-Bosch process for manufacturing ammonia that require fossil fuels as input directly to the process, so conveying energy but not in the form of electricity. So these are difficult sectors to decarbonize, and they're contributing a large amount of greenhouse gas emissions. The Haber-Bosch process by itself contributes about 1% of global greenhouse gas emissions. So the energy transition requires decarbonizing these difficult to decarbonize sectors, and electrocatalysts can help here by allowing low-carbon electricity to be used in place of fossil fuels or converted into hydrogen and other electrofuels. Is everything good with the recording? Okay. So this is an important area of work that many in the room I know working on. However, the space of candidate catalysts is really big. And beyond that, even when you have a particular catalyst to evaluate for a particular process, the simulations traditionally used to evaluate that catalyst are slow to run. So many possibilities, and for each of those possibilities, really slow to evaluate. So traditional simulations using density functional theory are computationally expensive. So we're going to look at a couple of different tasks, but we're particularly going to focus on the data set involved in the Open Catalyst project, which is a collaboration between a number of researchers, including at Carnegie Mellon and at Facebook, who put together a data set and set of challenges associated to that data set to use machine learning methods to predict both the relaxed energy and the relaxation trajectories of an adsorbate catalase system to evaluate catalyst effectiveness. So there are a bunch of different catalysts which are involved here. There are 82 adsorbates, so it's a lot of different reactions. These are all involved in renewable energy to some degree. So for example, there might be the synthesis of hydrogen. There might also be using hydrogen as a fuel. There is the creation of ammonia, et cetera. So then the catalysts are, these are up to 3 elements per catalysts. And then these are arranged in in a slab. So there are different crystal structures for the catalysts with 1 to 3 elements chosen out of a set of 55, mostly metals. There are about 450,000 relaxation trajectories. These are computed using VASP. And then there are about 120 million individual steps in these relaxation trajectories. And so one wants to basically do it much faster than VASP in order to evaluate either, and I'm not going to go into the full set of tasks here, but there are a bunch of different versions of this where you can either try to predict the relaxed energy directly, or you can try to predict forces at each particular point in order to get stepwise to the relaxed energy. So you can say, oh, well, let's predict the forces at this moment, move it a little bit, then move it a little bit, do a bunch of different steps in order to get to the relaxed energy. Or, the deep learning philosophy is let's just jump directly to what we want. So let's just jump directly to the relaxed energy. OK, so some popular strategies here include invariant and equivariant graph neural networks, such as all of these, like SCH and DynetNet++ and blah, blah, blah. Let's dive into a little bit what these things are. So graph neural networks for molecular modeling. Graph neural networks are a way to use deep learning methods on graphs, basically. Deep learning being roughly equivalent to neural networks. So GNNs, graph neural networks, are iterative. At each step, there's information associated to each node. That's called a node embedding. And this is a vector for each node. And then there's also information associated with each edge, which is an edge embedding. Sometimes there's also universal features for the entire graph, though we're not going to be thinking about that. At each step, each node embedding is updated based upon the previous state. Sorry, it should say state, based upon its previous state. It has a memory of 1. And then the states at the neighboring nodes. So it's considering sort of the local structure of the graph around that node. And then the update function is actually trained as a neural network, which is why it's a deep learning method. Meanwhile, each edge embedding is updated based upon, again, its previous state and the state of the node embeddings incident to that edge. So if you have an edge, you can think of an edge as a bond, though there's a reason why I'm not saying edge equals bond, which we'll get into in a moment. But if you have a graph more generally, you have edges between the nodes, and then the edge states are going to update based upon what's going on at the nodes, vertices connected to that edge. So the same transformation, importantly, is applied at every node and edge, so this generalizes across different graphs. So this is fundamentally why this is good for graph structured data, because it generalizes across different graphs. You can do the same thing even if you change the graph and the neural network has never seen that graph before. So the overall process for using a graph neural network in this kind of context is you get some data, you're going to take, and there's going to be some features associated with that data, and there are going to be spatial configurations associated to it. This is in the particular context that we're working with, sort of if you have some atomic level information. You're going to create a graph. You're going to have to create embeddings for the various information that you've got at nodes and edges. You're then going to run your interactions. This is this message passing procedure between nodes and edges. And then you're going to have to work out how to synthesize that into an output. OK, so I'm going to get into each of these points sort of piecemeal throughout the talk. But let me first talk about our first set of contributions. And they're going to be 2 main sections. So this one is called FAST, and then the next one is going to be called FANET. And these are sort of in parallel, though we're overlapping the techniques a bit, because we've been working on these 2 sets of improvements in parallel. So the contributions in the FAST component, we're going to increase both the accuracy and scalability of graph neural networks applied to catalyst discovery. And oftentimes, machine learning people will focus on the accuracy, but here we really need to think about scalability. Because remember, you've got to apply this to lots and lots of catalysts. In the most naive setting, you're really going to be applying it many, many times. And so having the ability for this thing to be as fast as possible is really important. And often neural networks get huge, and they get very computationally intensive. There's also an equity perspective. Like if people can't have the computational infrastructure to run this stuff, then it's a real challenge. OK, so the three things, hopefully you can read the top one. Can you sort of read it? Yeah, at least in the front. So the three things that we're going to talk through really quickly are a graph representation that's tailored to the task at hand. And sort of overall, the theme is let's build in more domain information into these graph neural networks. Graph representation that's tailored to the task at hand, richer physics-based atom representations, and an energy head that's learning a weighted average of per atom predictions. The motivation for thinking about these sort of specializations of a standard GNN architecture is, generally speaking, deep learning people don't care about the data at all. Right? Like, I say this coming as a deep learning person. Like, generally speaking, we look at some data and we're like, oh, like, just give me this big matrix of data and give me some labels, and I'll try to work out what you want. I don't care whether it came from catalysts or from satellite imagery or from, this guy next door. It is just a question of some transformation of the data, and the neural network will learn it. Now, this is totally wrong in most cases, because you normally need to encode some more domain information, or you're throwing out most of what you need to solve the problem, or solve the problem most effectively. So here we're making these changes. And notice this can be applied to any graph neural network. In the next section, we're going to get a specific graph neural network. But this can be applied to anyone. And it's just basically to try to make any graph neural network better for this particular case. And we're going to find that these modifications improve accuracy by 5 to 8%, which is quite a lot. And they also divide compute time by a factor of 3 to 5. So it's monumentally faster while actually being more accurate. So the traditional pipeline for graph creation, this is the first step that we're going to look at, graph creation. So remember when I said that edges are not bonds? You might be tempted to think that edges are OK. You might be tempted to think that edges are bonds. And that would be great. But we're working here with like bonds that are breaking. And also, we're working with this big slab catalyst that doesn't have like necessarily well-defined bonds because it's metallic, right? So we aren't going to have edges representing bonds. We're going to have edges representing sort of proximity. So if you're close enough between two atoms, then that's going to give you a bond. Oh, sorry, not a bond, an edge. Confusing myself. So there are three tags. These represent the three different categories of atoms. There is the adsorbate, there is the catalyst surface, and then there's sort of deep inside the catalyst subsurface. Tag 0, tag 1, and tag 2. And this is how we're provided this stuff in the data set. And our first insight is we can forget about the subsurface, basically. Not completely. If we just got rid of that, that would be bad. But we can actually aggregate it into a supernode. We tried various other aggregation structures. This is sort of the end product of a lot of experimentation. So we did all the ablation studies to work out what works best. But aggregating into a supernode is great because it saves a lot of work in the graph. And remember, this is these graph neural networks are message passing. So the amount of time required goes up, not exponentially, but quadratically or more. Because you actually, some of these graphs even consider like triplets of nodes. And so if you have more nodes in your graph, it really gets expensive. It's very computationally expensive. So we can get rid of a lot of the nodes just by aggregating them to one supernode. Is there a reason why it's falling asleep? OK. Anything I should do? No. OK, great. Maybe I'm boring the projector to sleep. OK, so that's the first innovation. Second innovation I want to bring up is physics-aware atom embeddings. And you might think that this is obvious, but people were actually not doing this. Previously, people were just throwing in the atomic number and learning sort of some vector based on that atomic number. This is, again, the deep learning philosophy. Oh, we can learn everything from scratch. So we don't do that. We throw in where in the in the configuration it is. So is it part of the adsorbate or is it part of the catalyst? It might be either one. Like there are some, oxygen might be in either one. Atomic number, which is what this was there before, we throw in physics attributes like electronegativity or the atomic radius, because why was that not included? We throw in the grouping period as well. And it turns out these are all really useful. And then the third component is atom-aware output pooling. This is a little bit more technical. It's also not that important, so I'm going to go through it really fast. Basically, when you've got a graph neural network, you've got predictions at all these different nodes in the graph. But you need to then aggregate that into one overall prediction for the energy. And so what people were doing before was they were getting a prediction at each individual node, and they were just summing them all up. And there's no really good reason for that, because that's not how energy works quite. So we instead, at least, like the sort of simplest way you could go up from that, we tried various other things, is just a weighted average incorporating the atom identities, so that it's not just a sum. And maybe you have a hydrogen, and the hydrogen's not going to contribute very much at all. Like it couldn't contribute very much to the relaxed energy in any way, just because it's pretty unimportant. And so maybe you have a weighted average incorporating the atom identity. So that's what we do. We just learn the weights for a weighted average, which incorporates like the particular information about particular atoms. Okay, so that is the first set of innovations here. Evaluated on Open Catalyst 2020, IS2RE. It's like the relaxed adsorption energy from the initial atomic structure, going straight to the energy. So there are various different ways that we can evaluate these. We can do in-domain, out-of-domain. I'm not going to go through all these different things, but the in-domain versus out-of-domain is basically how good is it generalizing to things that it hasn't seen before. Like it's out-of-domain in the adsorbate, out-of-domain in the catalyst. Like this is something new that it's never seen before. How good is it at generalizing? And then we're going to look at both the accuracy and the inference time. And then we're going to look at how this can improve standard models used in the field. I mean, the important thing is this is a general purpose framework. We can add it to improve stuff. If you've got a good model, this can make it better, ideally. And so we find this is exactly what happens. It consistently improves both performance and inference time. We're going to look at these three models. So you'll notice that one of these models is sort of much faster than the next one. This one is slightly more accurate. This one is sorry, I have a laser pointer. This one is slightly more accurate, but this one is much faster. And so what we can actually do, we're going to increase the accuracy of all of them. Each of these errors goes down. It's good to go down. It's an error, so smaller is better. And then the time also goes down a lot. And what we find is that sorry. Yes. So if you compare the sped up the fast version of SCHNet, it's actually basically as good as DimeNet++, which people were using because it was the most accurate. But we can take this faster version and make it as accurate. And this is like 20 times faster. The accuracy improvement is particularly big in the generalization setting. So it's particularly good at generalizing to things it hasn't seen before, possibly because we're incorporating all this physics information. And there's a particularly high amount of speed up if you look at DimeNet++ and ForceNet, because these are a larger number of hops. So SCHNet is a one-hop message passing approach where you consider only smaller numbers of nodes at a time. But if you have a two-hop message passing approach, then you're considering sort of the twofold neighborhood of a node. I don't really go into this, but this is to account for like angles and stuff. OK, so you can expect even better computational scaling on more complicated models. So like the more complicated the model, the better the improvement. OK, so that's the first part. Second part. Now we're going to look at why there were these complicated models in the first place, and can we make them simpler? So the motivation for a lot of these complicated models is invariance and equivariance. And what does this mean? So it's a challenge when designing GNNs for materials that the same configuration might occur in different orientations, right? So take the same configuration of atoms, turn it around, shift it around. It's the same thing, right? We should be able to build in that the model shouldn't care about orientation, essentially. So what does it mean to not care? There are two versions of this. There's invariance, which means that the output stays the same under transformation. So that could be if you're predicting energy, for example. Or it could be equivariance, which it could be, for example, if you're predicting forces, where if you rotate the model, or if you rotate the input, the forces they're not exactly the same because you've rotated the forces too, right? Like you rotate everything together. So equivariance means that the same transformation that got applied to your input also gets applied to the output. In practice, we often want invariance or equivariance with respect to rigid transformations of the input in 3D, including rotation and translation. So the traditional way to enforce invariance or equivariance is to build it into the model's representations. You transform the inputs so they don't depend upon the spatial configuration. So this might be done in a lot of different ways. You might have seen some of these, like radial basis functions, Bessel functions, Clebsch-Gordon tensor products. It rapidly gets kind of complicated. And some of this is super useful, and some of this is mathematicians wanting to use complicated math, speaking as somebody with a math PhD. Yeah, sometimes it's our fault. However, it can be really computationally expensive to do these things. The kinds of transformations that you need to make the inputs be truly invariant or equivariant can add a lot of computational overhead. Moreover, it's kind of hard to understand, and it really limits the kinds of things that you can do with the model. Since the model is becoming more complex to deal with this overhead, it can't do various other stuff, and it may change the kinds of functions that are expressed by the neural network. This is an example of one of the architectures that gets used. Look, the only thing you need to take away is it's pretty complicated. All of them get pretty complicated, and to some extent that's inevitable. And it's a really good architecture. This is not me saying that these are bad, but in certain applications you want it to be simpler. So what we're going to do is I'm going to gloss over some of the details here, because this is basically representation theory, like simple representation theory. So one can make a function equivariant with respect to transformations, which should be one word, via symmetrization. And so this is sort of the naive thing that you can do there. What that means is that you just average across all the transformations. So going to something completely different, if you were looking at, if you know about the AlphaGo algorithm, which was an AI algorithm designed to perform well in the game of Go, what they did was they wanted it to be invariant to, or equivariant to, the configuration of the board. And so they averaged across the data caused by like reflecting and rotating the board in different configurations. And you can do that if your set of transformations is finite, because there are only a limited number of things to average over. But what do you do if the number of transformations is actually infinite? Right? Like you can rotate and translate as much as you want. It's not a discrete set. So basically, there's a way to deal with this. There's a frame averaging operation. It looks like this. This is your function of interest, in this case a neural network, and there are group representations that are just, think about how the transformations are acting on your data, both before and after it goes into the neural network. What we're going to do is we're going to basically take out some particular configurations, and these are going to be, you're going to think of these as frames. Again, I'm not going to be able to go into the details, but we can take out a specific small set of frames and just consider the average over those frames. And in this case, what we're going to do is we're going to define a frame by taking the principal component analysis of the data. And so this is going to define something that is that doesn't change based upon the configuration of the atoms. And we're going to use this frame in order to find just 8 configurations to average over. And it turns out we only need 8 because of the particular nature of the group E3 of transformations, of rigid body transformations in 3-dimensional space. So we've gone from infinitely many things we need to average over to just 8. And then there's going to be an even cheaper form of this where we don't average over 8. We just pick one at random. So this is basically a data augmentation technique with post-processing in the case of equivariance. Again, I'm not going to go into details, where the space of augmentations is very small, importantly. And then I can quickly go through the architecture. It isn't still that simple, but it gets a bit simpler. We are learning atom embeddings based upon physical properties. Again, we're learning edge embeddings to capture three-dimensional geometric information. Importantly, we don't have to encode our positions of atoms in some special way with like special bases. We can just throw in the normal basis representation of our spatial information. And this is fine even if it breaks symmetries because we've dealt with it with the data augmentation, the frame averaging. For message passing, I'm just going to gloss over this. This is just how we combine messages at the level of edges and nodes. And then we're going to do two different things depending on whether we're predicting energy or predicting forces. For energy, we want it to be invariant, and so we're going to just sort of glom everything together in a particular way. And for force prediction, we are actually there's going to be some component of the frame averaging which has to be looped back. And again, I'm not going to go into the details to deal with the fact that we want the forces to be equivariant, to change when you change the input. We're going to train the model using L1 loss on the energy, so just how far away it is from the energy, and L2 loss for the force predictions. And the important detail I do want to mention is because forces are being predicted directly, they are not guaranteed to conserve energy. Many of the methods that are used in the space deal with this in other ways. They deal with this either just by ignoring it, or they enforce conservation by computing the forces as the gradient of the energy. So you can say, predict the energy, and then compute the gradient as you change position. So this is a reasonable thing to do, but it's actually pretty computationally expensive. It's very computationally expensive at inference time, importantly. If you want to run this model, it takes a lot of time. But what we would like to do is we don't care how long it takes to train the deep learning model, to adapt it to fit the data. All we care about is how fast it is to run on some new data. And so we create a computationally intensive loss that says, OK, we're going to not move too far away from these gradients at training time. And so we're going to try to predict something that basically conserves energy. But we're not going to enforce it strictly, because that will be computationally expensive. And so we add this sort of don't violate energy conservation too much at training time. And then at test time, there's no computational overhead. So we do some experiments to verify how well this works. We look at both stochastic frame averaging, where we're taking just one frame instead of taking all 8. And we do indeed find that both full frame averaging and, in practice, the stochastic frame averaging do achieve equivariance and invariance. And we're going to look at this across many different tasks, actually. We're going to look at this on OC20, but we're also going to look at this at QM9 and QM7, which are sort of standard molecular property prediction tasks. OK, so this is the figure of results. I'm almost done. Basically, we find that this FANET framework enables you to be basically optimal with respect to both speed and accuracy. So this is on OC20. And so you can see on one axis, this is the accuracy. So lower is better. And this is the speed. So higher is better. So it's throughput. So the fastest model is over here. Most of the models are over here. But the fastest model previously had a huge loss in accuracy. And so we're actually better than everything else. But we're almost as fast as the fastest model. And then the same thing holds true in QM9, where if you look at this is the MAE improvement in this case. So higher is better here. And then here, this is the relative compute cost. So lower is better. So here we find that, again, we are basically as fast as the fastest algorithm while being as accurate as the accurate algorithms. Great. So we have the right trade-off. In conclusion, what are we going to use this for? So we've designed some effective and fast ways to approximate the relaxed energy for individual adsorbate catalyst pairs. And what are we going to do with this? Well, we are building generative models that are going to search over the space of catalysts and spatial configurations of catalyst adsorbate in order to make use of this information. We can use these fast evaluation techniques to generate good catalysts. And so our graph neural networks provide fast oracles to train these generative models, while standard DFT simulations are also important, and they provide sort of more slow but also more accurate oracles that can be used as well, a combination of these. That is all I have, but I want to point you to the papers where we talk about this in more detail. First, FAST, which is already up as a preprint. Second, FANET, which is about to be released as a preprint. This is sort of hot off the presses. We've just finished this work. I think there are a couple of minutes for questions, and thank you.
Yeah, I see a few questions.
Please.
Thank you for the nice presentation. I have two questions. The first one is, are you using also dynamic graph neural networks, or?
I'm sorry, are we using?
Dynamic graph neural network, or because the dynamic one will consider the input change through time.
Like the graph being dynamic itself? So at each step, the graph is fixed in the sense that if you have computed even if you're just computing one sort of move, the graph is fixed for the course of that move. So I think, does that answer your question? So I don't think there will be a need to consider a dynamic graph quite.
Okay.
But I'd be happy to talk about this more offline.
Okay. So the other question is related to the inference time.
Yes.
So did you use a specific hardware, or what was your methodology for that?
This is a great question. So we have gotten significant speed-ups on both GPU and CPU, and importantly, there are, I don't have slides for this, but this makes it computationally tractable on CPUs in a way that wasn't before, which is great.
Okay.
Yes.
I have a question on the input files. So I'm doing myself a lot of VASP calculations.
Yes.
And when you speak about 450,000, like just relaxed geometries, is there like a standard for the input file, like for the in-car file?
Yeah.
That you need to simulate? Because like if you different K points means energy like different energies.
Absolutely, but I don't understand that. Since I'm a computer scientist.
So is there a standard just in general to have it? Like, or do you just take everything? Because let's just say, like, if you have a calculation of a single gamma point, and then you go to 2 K points, the energy difference is almost 2 EV.
I would point you to the OC20 papers for answers to these questions. I'm sorry, I don't know.
Okay, because that was the follow-up question. Because when you speak of your accuracy, having an accuracy of 600 MeV, it's a lot of, like, you can have the molecule sitting in a lot of surface sites with that difference in accuracy. So that's why I was wondering if there's already a link between like inaccuracy of the input file and accuracy of your output that you gain.
Did you want to say something, or?
Yeah, I can say something.
Please, yeah.
We studied these papers very extensively.
Great.
So great papers.
Mm-hmm.
So one of the simulation, the data, how it is collected is mentioned how it is collected. So they have taken consideration of K points. And of course, some of the simulations did not converge, which is expected. So they tried to redo those calculations to generate, to converge, to get the relaxed energy. But I think they considered K points, not gamma points.
Yeah, sorry, the gamma point is just 1 K point.
Yeah.
That's why I was on.
Different set of K points based on the material, so that was very impressive to
Okay.
see that they converged the structure the way we work in the DFT.
Okay.
But they considered spin polarization as well. It's impressive to see that. Of course, there are some loopholes, some of the things that did not converge, but those are always there, right?
I think there was one more question here.
Yeah, just one more question. We have to take this.
No, come on. I have
Well, we are doing this way, but I want to hear the students talk.
Hi, thank you for your presentation. In the starting, you said that you have an application in agricultural. So in starting slides, you have...
Yes, this is not of this stuff, to be clear.
Yeah?
This is not an application of this work to agriculture.
Yeah. No, in starting you mentioned that you have, yeah, forecasting, predicting agricultural yield.
Yes.
So I really don't understand that how the simulation and everything can predict the agricultural yield.
So this is our other work. This is not the particular models that we're talking about here. This is other algorithms that are taking satellite imagery as input and predicting the crop yield based upon pixel values at a particular point. This is joint work together with NASA Harvest, which is the agricultural remote sensing arm of NASA.
Okay, thank you.
No, absolutely.
Thank you. Nice presentation, thanks. I've seen you mentioned Uber gas tiger in work for, I guess, platinum catalyst. Do you work with Germany right now?
Sorry, do we work with Germany?
Yeah, I've seen an article with gas tiger, with a model you showed, an article in 2021. I'm just wondering, because you showed this model, do you work with him or is it just
Sorry,
an
with
example?
whom? Sorry, I still didn't hear. Oh, Jeremy?
In Germany.
I think
You mentioned an article
Which chart? Sorry,
with
which-
gas tiger in 2021 in your slide,
Oh, when did I?
close to the end.
Sorry, I'm not sure. Oh,
Here.
no, we don't work with that
You
group.
don't work.
We don't work with that group. Yes.
Okay, because I guess it's a platinum catalyst. Because I know this guy because I worked on the
No.
past on fuel cells, with platinum.
It's a great algorithm. We were trying to see how we could adapt methods like this and make them even better. That was sort of the point of FAST.
Okay.
We weren't trying to just supplant them.
Okay, excellent, thanks.